Welcome back to Science for Skeptics. I Can Science That, and I'm doing a series intended to dig into density and buoyancy and weight and where it all comes together, how it fits together. Last time, link up there, we looked at a law of relative density. This time, we're going to explore some of the limitations that law had, try to extend it to account specifically for direction, and that is, why does weight pull us down? Where does this down coming from? Last time we left off with the law of relative density. This is an equation, not an explanation for where weight comes from, but an equation that allows us to predict what the weight of a given object will be. The reason that's valuable for us is we can look at this mathematical expression and see which elements seem to be important in creating the weight of an object. And what we discovered by measuring them was that, of course, the volume of the object is directly related to its weight. Doubling the size in volume of an object will double the weight of the object. And the same thing holds true for things that float. The buoyancy of the object is also related directly to the volume of the object. How about these rows here, these Greek letters? These are the density. This is the density of the object. And we see from this equation that making the density of the object greater will cause it to weigh more. Making the density lower will cause it to weigh less. How about this term here? This is the density of the medium. If we were to reduce the density of the medium, we would increase the weight of the object. We see that from the minus sign here. Conversely, if we were to increase the density of the medium, we would reduce the weight of the object. If we had an object less dense than the medium it's in, this subtraction would come out negative, and that would predict a negative weight, also known as buoyancy. That object would float. So we put helium in here for rho sub O. We put air in here for rho sub M. We find helium floats up. Okay, so that tells us the important terms of how to predict the weight or buoyancy of an object. We can determine whether an object will sink or float in any given medium and how much weight it's going to push down on a scale or lift upward. If this is a helium balloon we're putting in here, we can actually predict how much weight that helium balloon can lift if we know its volume, and we know the density, and we know also the density of the air that it's floating in. Okay, that leaves one term on here to explore, and that is this constant. We need to measure from nature what the relationship between weight, density, and volume is, and when we measure it, we'll fill that number in right there to see what the relationship is. In the previous video, we measured and we found that the value of K for different objects in different mediums always comes out around 1.0 grams of force per gram of mass. And that was consistent. So Mother Nature pulls down on objects with 1 gram of force for every gram of mass, multiplied times the relative density with the medium that it's in. If you mention relative density to a glober, what are they going to say? They tend to say pretty much the same thing. They ask, if it's all about relative density, why do things go down? Density doesn't have direction to it. Where's the direction coming from? Well, let's take a look at this equation here and see if we can address that. Weight, the weight of an object, is directional. Weight pulls down. Heavy objects sink downward in lighter mediums. Lighter objects float up. We know that it goes up and down. It's specific to a direction. But the globers are correct. This equation doesn't have any direction to it. Density is not directional. Density is the same in all directions. It's density. Volume also does not have any direction to it. We need to get something added to this equation to give us that downward sense so that we can make weight be a vector. Now, in mathematics, we're going to introduce the concept of vectors and scalars. A scalar is just a value that has a magnitude. It's not a vector. It's just a vocab word, scalar. A scalar just has a magnitude, doesn't necessarily have any direction to it. A vector, on the other hand, is a specific mathematical term that means this thing has a magnitude and a direction.
Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
We know that weight, being a force, has a downward direction to it. If you step on a scale, measure yourself, you weigh a particular amount of downward weight. There's a direction to that and a magnitude. Therefore, this weight is a vector. In mathematical notation, we'll write an arrow over that. An arrow symbol over that will indicate that is a vector term. That term has both magnitude and direction to it. Now, these other terms, volume and density, they do not have any direction, so we will not put arrows over those. That just indicates those are scalars, which means magnitude only. Okay, but now this equation is wrong because we have a vector on the left-hand side and we have a scalar on the right-hand side. When you multiply two scalars, you just get another scalar. Nobody gave us any direction. There's no direction on the right-hand side of this equation. All the direction is on the left. It's not balanced. We need to fix that. We cannot make density be a vector. We cannot make volume be a vector. But this K value, the K value is just something we measured from nature. And we have seen that in nature, heavy things go down and light things go up. So when we measure K, we will simply measure it as a magnitude and a direction. That makes our K vector a vector quantity. So now we have upgraded our law of relative density to handle vector notation. This is a directional formula, and it will continue to work. We will simply measure K, which we found to have 1 gram of force per gram of mass. We will also measure the direction of that gram of force. That direction is down. If rho sub O is greater than rho sub M, the weight will point downward. If rho sub O is less than rho sub M, that weight will point upward, the opposite of downward. It will take the direction down from the K vector, which is just a value from Mother Nature, multiplied times the relative density times the volume of the object, will get the net weight of that object in that medium as a directional quantity. Putting that into vector notation, we have this format where the law of relative density now shows that weight is a vector. Weight is a vector that points down. And where does that downward come from? In the equation, we can see that it comes from our K vector. Doesn't explain why, but we measured this K value from nature, and it showed us that for some reason, nature wants to pull things downward. This is one of the reasons I insisted in the previous video that we keep that K. Despite the fact that it was measured to be 1.0, we needed to keep it to keep our units, but also we see now because the K is how we get the direction into this equation. Now, this equation, what good is it? First of all, it allows us to predict the weight or buoyancy of different objects, and that is inherently valuable. But from a science perspective, I want to look at this and have it guide us where we should look next. The direction of down, the question the Glober asked, where does it come from? Well, it didn't come from the density, and it didn't come from the volume. It came from this value k. That tells us if we want to know more about the direction, we need to explore k. We need to design experiments that measure what k is and see if we can find anything that causes k to vary. Those things will lead us towards the cause of this downward force.